Hello and welcome to a video about forces and elasticity, and we're going to look at how forces affect various elastic objects, and we're also going to look at something called Hooke's law, which in this case we're going to look at how it affects a spring. Now to start us off with, we can look at a few elastic objects, and if we take the first one, this is just a regular spring, and what you can do is you can stretch that spring and it becomes longer. Now if I just hook it onto this little hook down here so it stays. What I've done here is I've stretched the spring and I have actually done work on the spring. Now in physics, work means to transfer energy. Spring. So work means to transfer energy. So what I've done by pulling this down is I've transferred energy to the spring, and that energy is now stored in the spring as elastic potential energy. Okay, so we have the elastic potential energy stored in the spring, and I've managed to store it in the spring by doing work on the spring. And what I did was I transferred energy, and all I did was I pulled it down and hooked it onto this little clasp at the bottom there. Now if I want to release that energy, all I do is unhook it, let it go, and you'll see that spring will release that elastic potential energy that I've stored in it. It works in a similar way to other kinds of spring. This one can be stretched, but it can also be compressed. So I can squash this spring, can hold on to it for a while, and again I've done work on it, and I can release that elastic potential energy that I've given it just by letting it go, and it will spring back into its original shape. This is an elastic band, and similarly you can pull it and transfer energy to it, do work on it, and let it go and release that energy. I'm sure lots of you have done that before. And again with a ball, you can squash the ball, do some work on it, give it some elastic potential energy, and that actually is quite useful in the ball, because when it bounces on the ground, that's exactly what happens. You get squashed slightly, work is done on the ball, elastic potential energy, and then on bouncing upwards that energy is released and allows it to bounce back up again. Okay, so that's the sort of overall idea about transferring energy to springs. I've used springs, a rubber band and a ball, and the specification says it talks about transferring energy to elastic objects. Okay, now what we're going to look at next is this idea of Hooke's law, and this usually talks about the stretching of a spring. Now it can actually work on any elastic object, but if they give you something different to a spring, they will clearly tell you that it behaves in a similar way to a spring. Now, what is Hooke's law all about? Well, it's about this sentence here. It says the extension of an elastic object, often we use springs, but here it says the extension of an elastic object is directly proportional to the force applied, provided the limit of proportionality is not exceeded. Now that sounds like quite a complicated sentence, quite a fancy way of saying some science, but if we break it down, it just means basically the extension of an elastic object, so how much something stretches by, so the amount of stretch of an elastic object, so it's these kinds of things here, but often remember we talk about springs, is directly proportional to the force applied. So that just means directly proportional means if you double the force, you double the amount of stretch, you double the extension. If you multiply the force by 4, you will have a 4 times extension on your spring. The last little bit says provided the limit of proportionality is not exceeded, and this is talking about when a spring is overstretched. When you overstretch this spring, it permanently stays overstretched, and it doesn't actually then follow this rule that the bigger the force, the bigger the stretch. Okay, so once we've overstretched it, it won't work anymore. Now what we need to be able to do, or what you might have done before in class, is to do an experiment to test out Hooke's law. Is it actually true that the more force you put on this spring, the more it stretches, and in fact, is it proportional? And you might have done an experiment that looks a little something like this. You've got a ruler, a spring, and some masses, and these masses will actually provide the force. Okay, so each one, let's just say for argument's sake, is 2 newtons, that's 2 newtons, that's 4, 6, 8, don't know why I haven't got a 10, and a 12. 2, 4, 6, 8, 10, 12. Okay, so what we do is we take our first mass, which will give us a force of 2 newtons. Remember, mass and force aren't the same thing, and there's another video about that you can go and watch if you're not quite sure. But we can take our first mass, hang it on the spring, but before we do that, we have to get our start point. It's important that we are measuring the stretch of the spring and not the length of the whole spring itself. So our start point here is 0. I've lined it up like so, and then when I put my first mass, not my first numbers, my first mass on there, you'll see that the spring extends by 5 centimeters. So I've gone from 0 to 5, so for our force of 2 newtons we have an extension of 5 centimeters. Similarly, I can then go on to my next mass. I can add that on. The extension is now 10 centimeters, so it's extended or stretched by 10 centimeters. So I can put that on my graph. 4 goes up to 10, and I can go through my forces, putting those on, and I'll get a graph that looks a little bit like this. So as we go up, the amount of stretch, the extension, is directly proportional to the force added. But what you sometimes see after a certain point is this happening. Okay, so for this region of the graph, let me just draw it in for you. So for this region of the graph here, the spring is no longer behaving like it did there. So if you double the force, or if you add the force, it doesn't go up in a proportional manner. And at this point here, we can call that point there the limit of proportionality. That just means after this point here, if you add more force to the spring, it doesn't go up in a proportional way. So that's the limit of proportionality there. But for this region of the graph here, all the way up to just over 8, let's call it 8, if you double the force, you double the extension. So if you go from 2 to 4, it's gone from, the extension's gone from 5 to 10, and if you go from 4 to 8, it's gone from 10 to 20. So that works out quite nicely. Now if they were to ask you about this in the exam, I would guess they would use a spring. I did write to the exam board and ask them if they would ever use an elastic band, and they wrote back to me and said they might do, but they would have to say that it would follow the idea of direct proportionality and have a limit of proportionality. So I'm guessing they would probably stick to a spring, but remember, it could apply to elastic bands or even just curled up wires as well. And the last thing I want to look at is the actual formula that we're given that goes along with this graph. It goes a bit like this, and you will be given this in the exam on the formula sheet. But this is force is K times E. Now the force, quite simply measured in newtons. K is what we call the spring constant. And the spring constant applies to particular springs. So one type of spring will have one spring constant, another one will have another one, but it will always be the same for one particular spring. And the last letter here, this is the extension. And if we're being consistent with our units, I should have said force there, but if we're being consistent with our units, this is newtons. The spring constant is Newton meters, and extension is in meters. Okay, so that's the formula that you should be able to use. You will be given this formula. They won't necessarily tell you, no, in fact they will tell you what they stand for, but they won't give you the units. So let's have a look at a couple of questions that you might have, an easy one and a slightly less easy one. First one is a spring has a spring constant of 1000 Newton meters and extends by 0.25 meters when a force is applied. Calculate the force applied. Okay, so all we do is plug in our numbers into our formula. So it says here a spring constant of 1000. So force is what we're trying to find. F equals 1000 times, and the extension is 0.25 meters. And that, if you just bang it into calculator, or you should be able to do that really, is 250 newtons of force. So the force is 250 newtons. Now, slightly more difficult, but not hugely more difficult, is this question here. It says a Newton meter uses a spring to measure force. If it has a force of 20 newtons applied, how much will the string extend by? The spring constant is 1000 Newton meters. So again, just plug everything into the formula. We know the force, so it's 20 equals, then the spring constant is 1000, so it's 1000 times E. We don't know what E is, so we have to rearrange this formula, and if your math skills are really good, you'll realize that this is easily rearranged. 20 over 1000 gives you E, and if we work that out, the extension is 0.02 meters. Okay, so it extends by 0.02 meters. That's about 2 centimeters, and that actually seems about right. Okay, so there's a couple of questions there. We've gone over this idea of doing work on the spring and storing elastic potential energy. We've looked at a Hooke's law experiment as best we could, and we've done a couple of questions. So hopefully that clears things up a little bit for you, and thanks for watching, and see you again soon.